you now have the second part of my presentation. The topic will have a small overlap with the talk 2 days ago, where I was giving an introduction to multifluids. Today I will give an introduction to a technique to study multifluids, not exclusively multifluids, but it's particularly useful for multifluids, and that's second harmonic generation. You will see why this is a useful technique, and I will present a couple of examples. Okay, so let's start. That's the outline, and I will begin with an introduction to second harmonic. So there are plenty of methods to study matter. This, for instance, is any X-ray diffraction theta to theta scan taken from the literature, which then gives you a certain crystallographic structure. And this is extremely powerful. And you might ask, why do you need another technique? Why something like nonlinear optics? But there are a couple of reasons. So here are some of them that motivate us. One is that not all the techniques for studying the structure of matter will give you spatial resolution. Neutrons, for instance, are not, it's extremely powerful. You have the direct interaction between the neutrons and the spins, but it's a diffraction technique. Therefore, by nature, not spatially resolving. And here is one of the very, very few examples where someone has scanned a sample with neutrons and done diffraction, and then accumulated over 24 hours an image of the domain structure. But you see, 24 hours, 100 micrometer resolution. And it might be better, or it would be better to have another technique there that does it in minutes, for instance. Then you've heard a lot about interfaces, LAO, STO, and so on yesterday, and the other days. It would be nice to have a technique that is specifically sensitive to the surface or the interface and nothing else. So if you measure an integral technique, if you take an integral technique, you measure the entire bulk, and then the surface is just a small additional contribution. And it would be nice to have a technique that sees the surface only. Third, even a technique as powerful as neutron diffraction might have additional accidental degeneracies. For example, a spin structure like this, so a triangle compensated structure like this and like that, they are not distinguishable by neutron diffraction. You can calculate that, and if you have such a choice, you cannot really answer it. What is it? So you need something else to give this answer. Then, if you study magnetization or ferroelectricity or even the combination multifluids, we talk a lot about switching. So how do we reverse the orientation of polarization magnetization? How fast do we write a bit? And that's exactly what also certain techniques can answer better than others. Optical techniques, for instance, they give you resolution, time resolution down to the femtosecond time scale. So you can monitor switching processes with this time resolution. And finally, of course, there are also financial issues. If you have an alternative to large-scale equipment, going to a neutron or X-ray diffraction source, if you have the alternative to do it on your table, in your lab, that's also welcome, of course. Okay, plenty of motivation. So that's the technique I will talk about for this hour. Second harmonic generation. How do we get there? So you all know this equation. You have an electric field that you apply to matter, and then the polarization is formed in response. It's just polarization proportional to the electric field. And that also works if the fields are oscillating at some frequency omega. Then the electric field will oscillate, the polarization will oscillate. And then of course you can say, okay, but this is just the first term in an expansion of the polarization with the electric field. So you can say there are also quadratic terms, cubic terms, and so on. Normally they wouldn't matter because these are weak, as it is in expansions, so the higher order terms are weaker. But imagine you take a very, very strong electromagnetic field, like a laser. Then these contributions might start to matter. And they may give you interesting information that the first one doesn't give you. So let's look at the very first one that is coming here on top, this one. And if you then add the frequency arguments, this exponential I omega t for the electric field and the second one, then you see the response has to oscillate at 2 omega. just because the product gives you 2 omega. And in a picture you could say, so your matter, any electrons, they absorb 2 photons simultaneously. That gets you up here, and then the emission is in a single step. Polarization, but then you have to get twice the frequency of the incident light. And that's it. That's called frequency doubling or second harmonic generation. You send in light at 1000 nanometers infrared, you get out 500 nanometers green. That's it. So why should you do that? First of all, where does it come from? So it's as so many things as the multifluidics, it's not new. In fact, the really first work on nonlinear optics goes back as far as 1931, when Maria Goeppert-Meyer theoretically said there should be elementary acts with 2 quantum jumps. 2 quantums are absorbed simultaneously. Exactly what I just presented. And she wrote a paper about that. And the reprint for this paper was for sale at Christie's, so keep your reprints if you still have any. Makes a good price after a while. That was 1931. And the first experimental work demonstrating second harmonic generation is shown here, optical second harmonic generation. Generation of optical harmonics, Franken and co-workers, 1961. So you see, this is one of these ideas that was around for a long time, since the 1930s, and people simply didn't have the tools to make it. Like with planes, people knew how to make planes long before they actually had planes, because they had to develop the motors. Here they had to develop the lasers. And right after the development of the laser, someone said, okay, let's direct our laser beam onto quartz, 700 nanometers, that's the big spot from the laser, and then you get emission at 350. Half the frequency, half the wavelength, twice the frequency. And that's the famous paper that demonstrates it. There's an interesting anecdote about this paper. It's completely wrong. Because there is no spot here at 350, right? So there is the big primary laser, but there is no spot here. So what happened? So in those days when people published papers, they sent figures, but not electronically, they sent photos. And these photos had dust speckles. And there was the department that removed all the dust speckles and beautified the pictures, and the guy doing that, he removed all the dust speckles and he also removed the dust. And that's really happened because I once saw the original photography. There is a big slightly brighter spot here. So that's what happened. But everyone could verify that the experiment was true, so there was never an mirage. Okay, that was 1961. Then, much later, it was realized that this frequency doubling, it's applicable to ordered structures, and symmetry is a very important criterion here. So, to have such a process, this chi contains the information about the material, and the material has a certain symmetry. And symmetry tells you, like if you send in X polarized light at omega, then what is the polarization of your 2 omega light? And that is very, very specific. So if you see a certain emission at 2 omega, then you can say a lot about the internal structure just on the basis of the symmetry of the material. And then we are almost at the multifluidics, because you can then think, so how does ferroelectric order and how does magnetic order change the symmetry of my material, and which frequency double components would that allow? And typically you find that these are differently polarized from those. That means by looking at differently polarized second harmonic emissions, you can say, okay, this polarization gives me information about the ferroelectric structure, this polarization about the magnetic structure. And that's the best thing you can have. You see in a single material with the same technique, the electric plane structure, the magnetic structure, and therefore also the magnetoelectric coupling. It's ideal for looking at multifluidics. That's why I'm talking about this here. So this is the first experiment where someone used it, not just for generating frequency doubling, but for really imaging or detecting magnetism. It's second harmonic generation on iron. Iron is ferromagnetic. So what did they do? They just measured the emission, the second harmonic emission for plus and minus magnetization generated in the iron, and you see there is a small splitting. It's not great, but it's there. Statistically significant. And when they oxidize the surface, the splitting is gone. So this must be due to the magnetic order. So you have a magnetic contribution generates the splitting, and you have a non-magnetic contribution, the other one, and that generates the background. That's one of the first experiments, 1991, so it's not that long ago, considering that 1961 was the first demonstration of SAG. And then you can also detect antiferromagnetic structures, something that is notoriously difficult. So to those who have not so much background in antiferromagnets, you have a compensated spin structure, like here, up, down, and you have domains, like in ferromagnets. There is no magnetization, nevertheless you can have domains. So up, down is different from down, up, up. And here you see you have the two signals, one from the magnetic, one from the crystallographic order of this compound chromium oxide, which has this spin chain. The crystallographic order, it changes a little bit with temperature, the second harmonic signal, but nothing dramatic happens at the ordering temperature. This is shifted somehow, it should be here. So the nail temperature is here, the ordering temperature. But the red one, this continuously decreases, and right at the ordering temperature, 308 Kelvin, it's gone. So it indicates magnetic order background free. That's the nice thing. Even antiferromagnetic order, which is very difficult otherwise. And then you can, because it's an optical technique, you can just image the second harmonic light just with a camera. The only difference is you just put a filter in that blocks omega and just passes to omega. Then you get images of antiferromagnetic domains of this type. And this is really otherwise impossible. So there is this neutron diffraction image, 24 hours, 100 micrometers, and here you can readily take 1 minute, take pictures with optical resolution, 1 micrometer resolution, and see the antiferromagnetic domain structure, and when you hit the sample above the ordering temperature, the domain pattern is gone. So this was 1959. That's a lab that you would have to set up when you want to do this. So here is our laser, femtosecond pulses, generating 120 femtosecond pulses. So this is a fixed frequency laser. Here you make tunable frequencies, and here is the cryostat with your sample and all the optical setup. One setup on this side, one setup on that side. And $500,000 or euros. Or million. Okay, one problem is that you measure intensities, not fields. So if you have two domain states rather, so like in this case, so you have a distribution of regions where you have this up, down, or down, up distribution of spins. How do you distinguish them? So these two domain states, they would give you plus P of, so they would give you a second harmonic light field, and the other domain would give it to you with a sign, minus P of omega. A minus sign in a polarization wave is a 180-degree phase shift. Exponential I pi is minus. But then when you measure intensities, it's all the same. So you cannot distinguish two domain states, but you want to distinguish them. You want to see the domain. So what do? You do this, you set up this addition to your setup. Here is your sample in some cryostat. It generates the second harmonic wave, coupling to the magnetic order, for example. You then image this light, this 2 omega light, and the omega light generated, so the 2 omega light generated here and the omega light that is left over, you image it onto another crystal where you again generate SAG, and this is a quartz crystal, anything that generates a second harmonic wave. And then you overlap the two, and then you have a fixed frequency wave here from your reference crystal, and you have the domain-dependent signal from your sample. So you would get reference SAG plus P of 2 omega, or reference SAG minus P of 2 omega squared. So by an interference experiment, you can generate this into more or less intensity. And then you have saved the phase of your light wave, which would be otherwise lost. And you can distinguish domains. Here is an example how this works. So we have a sample, any sample, doesn't really matter what it is. So it's magnetically ordered, antiferromagnetically, and you see it's a rather homogeneous brightness. You have some interference fringes because it's not completely parallel planes, the sample. You have some lines here, but generally the intensity distribution is flat. Then you generate your reference wave in a quartz crystal, looks the same. But if you overlap the two, if you add them up, then you get domains. Because you have constructive interference for one domain state, destructive for the other. And you get a very distinct picture of black and dark domains, black and white domains. And here you see this imaging, so to project the image of the sample onto the reference is very essential. If you don't do this, if you just send the light through, then everything blurs because your waveform propagates. So now we have all the tools. We can see magnetic order, electric order, you can see signs in your wave, phase shifts, and you can see domains and domain states. End of the introduction. Okay. Next point. So let us see how can we determine magnetic structures by second harmonic generation. How do we do this? So let's take this system. I've mentioned it already 2 days ago a number of times. Hexagonal manganites. So they have manganese with an oxygen bipyramid around the manganese. So 5 oxygen ions sitting around each manganese. Here you see these cages. And at a certain temperature these cages tilt. So you can see this ion, for instance, it tilts a little bit upwards. This one would tilt a little bit downwards. This one would tilt a little bit upwards. And these tilts and a couple of extra shifts, they make the material ferroelectric. Ferroelectric at between 1250 and 1650 Kelvin. And then you have these manganese ions, and the manganese also orders magnetically, and it does so in these triangular structures. So it's not collinear, but it's triangular, but if you add all the spins up, the sum is 0. So this is antiferromagnetism, no remaining magnetization. This magnetism comes on top at something like 70 to 130 Kelvin. So you have ferroelectricity, you have magnetism, so it's a multifluid. And you can even have rare earth ordering. So for those compounds, for those Rs that are dysprosium or holmium, erbium, thulium, terbium, they order at 5 Kelvin, roughly. So it's 3 types of ordering. In principle, even 5 types of ordering. 2 are a bit hidden. 5 types of ordering in one compound. Elastic, magnetic, and ferroelectric. Okay, so that's our toy system. And let's see what can we say about the structure with second harmonic generation. Let's look at this corner here. So we have one spin pointing outwards, one spin pointing inwards, one spin pointing outwards. And that would continue here. And there can be other choices. Here are all the choices. Here are the 2 triangles again. Here is the pattern that I've just shown you. Outwards, inwards, outwards. So exactly what I have shown you. That's one choice. So you can have 3 pointing in, 3 pointing out. Or you can have all pointing out. Or all pointing in. That's all different choices. So one choice is what is the relation between the spin in the black and the white spin. So the spin at the bottom of the unit cell and the spin at half the unit cell up. So that can be parallel or anti-parallel. Here it's anti-parallel, here it's parallel. Better is you compare them on this line. So here they are parallel, here they are anti-parallel. Parallel, anti-parallel. Okay, that's one choice. Then the spins can point along the x-axis or the y-axis. So here they are pointing along y, here they are pointing along x. So you have the xy choice and the parallel anti-parallel choice. 4 different structures already. And then you have the structures transferring from here to there or there to there and so on. So I told you have 8 magnetic structures and they all have a different symmetry. For those of you who are not familiar with these symmetry symbols, it doesn't matter. So they simply have, some of them have mirror planes, so if you mirror the structure it looks the same or it doesn't look the same. Others have certain rotations that conserve the structure or break it. So all these have different symmetry properties. That's the message. And these are just names. So if you have, the funny thing is, if you have these three structures, and those 3, neutron diffraction, which you would typically take for analyzing the structure, it cannot distinguish between these and those. So these compounds were discovered in the 60s, and until 2000 it was not really clear if they're ordered like this or like that. And that's really a bit surprising. Imagining that they are so already around for such a long time. Good. So, but then let's look at second harmonic generation. So second harmonic generation says, if you look at this structure, you can calculate that X-polarized ingoing light would lead to X-polarized frequency double light. For this structure, X ingoing X-polarized light will lead to Y-polarized outgoing light. And for this one, you would get a mixture of both. That's pretty simple. So the message is, you send in omega, you get out 2 omega. For all these structures on the right, you send in light, no second harmonic generation. So it's pretty simple. If you see second harmonic generations, it's one of these. If you don't see it, it's one of those. So that's very easy as a criterion to distinguish these from those. You don't have the trouble that you have with the diffraction techniques. So let's have a look. Here there are four compounds, or 3 rather. Yttrium manganite has Y-polarized ingoing, Y-polarized second harmonic, and none in the X component. So this is the spin structure. There's no degree of freedom. Symmetry is there or it's not. It's like being pregnant. You are pregnant or you are not. You have the symmetry or it's not there. Yeah, but that means if you see that, then this must be the symmetry. There's no other choice. And then if you take erbium manganite, you see the other component. X-polarized in gives X-polarized outgoing light. So you know it's this spin structure. Holmium manganite is an interesting case. At 50 Kelvin, it's this spin structure. At 6 Kelvin, it's that spin structure. And that's it. So you have answered this 4-decade-long question with no ambiguity at all left. And nevertheless, because it's this rather strange technique to determine structures optically, frequently there are papers in the literature claiming other structures, all spins out. It's not possible. It would require second harmonic generation being 0, this structure. But we see second harmonic generation. Their criterion is, with a large error bar, a certain position of the manganese ion. So is it a little bit below 1/3 or a little bit up? So it's a really fine measurement from which they conclude this. And here it's simple. It's, do you have a signal or don't you have a signal? Okay. So determination of magnetic structures, but let's not forget the compound is also ferroelectric. So you can also then take other polarizations of in and outgoing light. Here you see your magnetic order. This is the magnetic signal. It disappears at the ordering temperature, the magnetic one. And then here this is the ferroelectric signal. It has a different spectral dependence, and it's also looks different. And here the ferroelectric SAG signal, it disappears at 1250 Kelvin, and that's the ferroelectric ordering temperature. Here are the antiferromagnetic domains. Here are the ferroelectric domains, not in amazing resolution, but at least you see them. And they have a completely different length scale. So these are almost millimeters, and here it's more like 10 micrometers. And this took us really a long time to get there. So this one was done in 2000. This one was done in 2050. It's not so easy to measure second harmonic generation up to 1250 Kelvin and then be sure that you don't have any other temperature effects. This is why it took so long. But in the end, you see both structures, both domain patterns happily coexist in a multifield. And that's that one I already showed 2 days ago. So then you can take domain pictures, apply electric fields so that you make these ferroelectric domains a bit larger. And then you see that the ferroelectric domains here, that they are coupled to the antiferromagnetic domains. So you have a ferroelectric domain wall, you have an antiferromagnetic domain wall wherever there is a ferroelectric domain wall. You have additional antiferromagnetic walls, but as I said, wherever there is a ferroelectric wall, you also have an antiferromagnetic wall. And this was then surprising, especially because this compound does not allow linear magnetoelectric coupling. So this coupling between magnetic and electric domains must come from the domain walls. So that's an early work where domain walls, multifluid domain walls play some role. Good, but you can do more. Lasers also have this nice degree of freedom of time resolution. And you don't even have to go to femtoseconds to work with that. So here in the following I will present an example where we used time-resolved second harmonic signal to see an interesting switching of a multifluid. So the motivation for this experiment is this one. So there is a community that is interested in switching magnetism optically. So imagine you have your hard disk and you don't have to fuss around with magnetic fields to switch your bits, but you just shine in light and you reverse your bit. Like heat-assisted magnetic recording is a derivative of of that if you have early contact. And then there is a group in Nijmegen, and they showed that you can take a ferromagnetic compound, you shine light with a circular polarization onto it, and then you set either the bright or the dark domain state, so either plus or minus magnetization. They do this a lot and have a couple of great papers in that direction, but it's all ferromagnetism, naturally, because ferromagnetism is technologically really the dominant form of magnetization, but the majority of compounds in nature are antiferromagnetically ordered, and then you can of course ask, well, is it possible to switch an antiferromagnetic state with light only? It could be useful. So for things like exchange bias, so basically manipulating ferromagnetism with antiferromagnetism, that's exchange bias. Or there are many phases, superconductors, and a lot of other stuff that have antiferromagnetism in other states, that then is also interesting to look at. Even data storage concepts based on antiferromagnetic spin couplings are being discussed very recently. The challenge is you don't have a macroscopic magnetization, so it's not so easy to access and switch your antiferromagnetic state, and also not so easy to see what you've done. So that was the motivation. So we took an antiferromagnet that develops a spin spiral, and one of those, where the spin spiral also induces an electric polarization. Terbium-manganite, I mentioned it 2 days ago. It has this spin cycloid, so it's from unit cell to unit cell, the spins oscillate or rotate a little bit, clockwise or counterclockwise, and that generates a polarization up or down, one of these. And then we just illuminated that with a light pulse. That's what we got. So before and after, dark domain state, illuminated with light, it switches to bright. Bright domain state, so clockwise spin spiral, up polarization, switches to dark. And it's really not some weird effect, so when you then measure this area as function of temperature, exactly at the ordering temperature of this multifluid, the splitting disappears. How does that work? Well, that's pretty simple. It's a heat effect. So it's nothing fancy, it's a heat effect, because you can do the same with a femtosecond laser, nanosecond laser, or with a laser that's always on, so helium-neon laser. So it's independent of all that, it's just the intensity, only the incident energy that lets this switch. And that very strongly points to a thermal origin. So somehow you heat the system above the ordering temperature, while the laser illumination cools down, and then because of depolarization fields on the ferroelectric side, it orders in the opposite direction. And because the polarization is magnetically induced, you reverse the antiferromagnetic state via the induced ferroelectric mode. That's the model. Here's the simulation, Monte Carlo simulation. So we describe our material. It's in a yellow domain state, so clockwise. We heat the top layer up with a laser, or we heat it up in a computer. Then we let it cool down, and indeed you can find criteria that it then polarizes and therefore also magnetizes in the opposite direction. So that's nice, because now we show that we can switch the direction of antiferromagnetic order via the secondary electric order with an electric field, with a light wave. But of course, switching means you also want to be able to switch back. So how do we get from here to there, from blue to yellow, back? So if I heat this up again and it cools down, it would again give blue. So after one switching, it's over. Is there a trick to make it switch back anyway? And this is what we came up with. So we introduced two color switching. First, laser pulse heats the sample to a certain depth, cools down, magnetizes and polarizes in the opposite direction. Second laser is more strongly absorbed, heats up only a top layer, and reverses only the very topmost layer back to the yellow state. Blue laser would again bring it to the blue state. So we switch between yellow, blue, yellow, blue, yellow, blue at the surface, depending if we take the blue or, well, this laser or that laser. Here is the Monte Carlo simulation. So in the computer it works. It's great, good, but of course you want to do it in real life. And in real life it looks like this. So switch black to white, back to black, back to white, and so on. 100 times, 200 times, no problem. You don't switch the entire sample, but you always switch this region in the sample, continuously between dark and bright, or left-handed, right-handed antiferromagnetism, or polarization, down polarization. And the imaging is always with second harmonic because it can distinguish these two domain states. You can also write, so you can just scan your sample with a laser beam and then you flip the surface along the written line. You can write a cross line and you don't have any crosstalk, so it really only switches where the laser is, and then you can erase it again with the second laser. So that's a nice experiment, all optical, or yeah, purely optical switching of an antiferromagnetic state, done and observed with a laser and with nonlinear optics, so with second harmonic generation. Next example would be to go to heterostructures, interfaces, and domain walls, because, as I mentioned in the multi-fluids talk, all these confined systems, they gain more and more importance. To not look at the bulk, look at the interface, look at the domain wall, because interesting stuff is going on there, other than what you can do in the bulk. So let's take our favorite compound, bismuth ferrite, which, as I mentioned before, is the most investigated compound. And in principle, I wanted to present, so it has these 8 ferroelectric domain states and the long-range iron spiral. And we also learned that bismuth lone pairs create the ferroelectricity that can then coexist with this magnetic order, and therefore it's a multi-fluid. And in principle, here at this point, I wanted to show a great work where the domain structure of bismuth ferrite was investigated by second harmonic generation in Michel Verret's group. They have a paper that will come out in Nature Materials, and that's just the point. I thought it's already out, but it's not, and therefore I can't show it here. So they found some interesting photoelectric, photomagnetic effects, magnetoelectric control in bismuth ferrite, and analyzing the domain structure by second harmonic generation. But it will be out soon, I guess. Here now we have a different idea. So you have seen Ramesh's experiment. So he says, okay, so my bismuth ferrite is antiferromagnetic, but if I want to control ferromagnetism, convert it into ferromagnetism, I just put cobalt iron alloy on top. And the cobalt iron alloy couples to the antiferromagnetism of the bismuth ferrite, which then couples to the ferroelectricity of the bismuth ferrite. And by applying a cobalt iron alloy and a voltage contact, you can reverse the polarization in the bismuth ferrite, and thereby the antiferromagnetization, thereby the magnetization in the cobalt iron alloy. The only problem is, how do you see that you have switched the ferroelectricity beneath those electrodes? Because electrodes, they cover them up. So typically you would scan your sample with a force microscope tip, and then you would pick up the ferroelectric state, but once there are metallic electrodes on top, you can't see what is below anymore. So Ramesh's group, they solved it by then etching this away and having a look. So what happened to the domain structures when I saw my magnetic switching? But of course the new electrodes are gone, so it's destructive. And it would simply be nice to have a possibility to see this ferroelectric domain structure under the domains without removing the electrons. So that's what we then tried with second harmonic generation. Here, first of all, we see that a nicely grown bismuth ferrite film, bismuth ferrite, strontium ruthenate, dysprosium scandate, with a certain domain structure, in this case a striped domain pattern, gives a very specific second harmonic response. So if you rotate the ingoing polarization of the ingoing fundamental light at omega, keep the outgoing light, the second harmonic light constant, then if you rotate this ingoing polarization by 360 degrees, you get this shape. No, it's 360 degree SLG intensity dependence. If we take another domain pattern, now not with the net polarization, not in this, but in that direction, then you see you get a completely different second harmonic response. So second harmonic generation can exactly tell you what the domain state of your bismuth ferrite is from the polarization dependence. So then we took this stripe domain pattern that Ramesh's group used for this magnetoelectric switching, and well, as you can see, with the force microscope tells us we have this stripe domain pattern Then we put platinum on top, and that means you kill your force microscope signal, because platinum is conducting, of course, so you cannot see the domain structure anymore. But SHE still sees it. If the platinum is not too thick, you can send your light through the platinum into the bismuth ferrite, and you can still see the stripe domain pattern. Okay, so then let's do this experiment, the switching experiment. Zero electric field, here's our platinum. And here is our stripe domain pattern, as it shows up in the magnetic structure. And now that's the second harmonic response from the ferroelectric domain structure beneath. It's this other type that I have. This one. No. This one on the right here. Okay? Good. So now let's apply an electric voltage to our platinum. And then we see that, not very clearly, but we see that this double lobe here, no, this quadruple lobe, that it deforms slightly. So these lobes here, they get shorter, this one gets longer. And a second harmonic image would tell you that there is some extra light is showing up that wasn't there before. And if you analyze this polarization dependence, you can tell that in your ferroelectric bismuth ferrite, you have now induced 21% of a differently oriented domain stripe. And if you increase the voltage, you see it goes up to 35, your quadruple lobe deforms more. So we can look at the magnetic structure, the picture that I have shown in the beginning. We can look at the ferroelectric structure that is beneath and what it has really done in response to the voltage, without having to remove the platinum electrons. That's really nice. Okay, so then let's take some other examples that involve thin films. One of the technologically most relevant thin films, ferroelectrics, is PZT, lead zircon and titanate. And we have already seen it's piezoelectric, so you deform it and you get a voltage, or you apply a voltage and it deforms. And it's ferroelectric then. And for instance, you can send sound waves and detect a swarm of fish, and then the reflected sound waves would deform your loudspeaker or whatever sensor, and then you get a piezoelectric response. That's one reason why piezoelectrics are used. We grow nice PZT films of different thicknesses. And we also see that they are nicely deformed by the substrate. And then we look at the following aspect. So when you have thin PZT films, the polarization of the PZT is always out of plane. If you make them thicker, you also get in-plane contributions. And companies like IBM, they want to know this. I mean, they want to know, if I've grown a film, do I have any of these so-called A domains, or do I only have C domains? Polarization pointing out of plane. And that's not so easy to see. So again, we said, okay, let's take some of these films of different thickness. Below 50 nanometers, there should be single C domain, and above 50 nanometers, there should have some A domain component. And let's quantify that. So then we took two of these samples, a thin one and a thick one, and rotated them in the laser beam. So we changed the direction of incidence of our light, or on the other, which is easier, we rotated the sample. And then you can analyze which components of our frequency of our second harmonic light will couple to A domains, which one will couple to C domains. And you see the component coupling to the A domains is 0. So in this thin film, we really only have C domains. But if we take the thicker film, we get C domains, this parabola, this tilting, and we also get A domains, because now this black signal here is non-zero. And here you can see them. So these A domains, they are very narrow stripes in a C domain matrix. And as I said, companies like IBM, they want to know and control this. Okay, so then we did the following. We said, okay, let's pole our sample. So let's apply some voltage to our tip, and let's erase these A domains. So here you have these A domain stripes, not very well visible, but they are there. Here you have stripes. we scan our sample with a plus voltage and a minus voltage, and the stripes are gone, which you can see from a line scan. So if you do a line scan here, our piezo force microscopy response is flat. That means there are no stripes left. But if you take the same scan with the second harmonic beam, second harmonic has the advantage it sees the entire film down to the bottom. Piezo response force microscopy has a penetration depth of certain nanometers. I don't know exactly how much, but at least it cannot look down to the bottom. But second harmonic second generation does that, and there you see there's still an A domain left, because you have a slight hump here, which is indicative of this A domain, so this in-plane polarized PZT component. And yeah, there it is. And in order to verify that this is really the case, we did some scans by transmission electron microscopy. And indeed, when you go to the bottom of the PZT, where it connects to the strontium ruthenate, you see there is an A domain. Not visible to piezo response force microscopy, but visible to second harmonic generation. It's pinned to the interface. And therefore it's buried in the film. But here you can see it, and also optically you could see it. That's exactly what then puzzles a company. So they think we have polarized it, it's all nice, all C domain, we can work with it, technologically great, but somehow it doesn't work. Why not? Because they don't see that there is a domain at the bottom that interferes with your domain 1 movement as they want to have it. Okay. Then one very outstanding aspect of these pictures is that there is this extremely high brightness that you have at the edges of the areas that you have polarized in one or the other C direction. So why would there be such a bright second harmonic emission? In principle, in this configuration, you should see A domains. That's why everything is black. So you could suspect, maybe in your domain walls it's not A domain. Maybe it's maybe it's not C domain here. Maybe there is an A domain that you see and that it's generating the light. So that would, for instance, be possible if, unlike what was suspected first, that a domain wall in a ferroelectric really is a transfer easing-like, so a transfer from purely up polarization to purely down polarization. But maybe it rotates like this, and then you would have an in-plane component, even without having A domain. So you could have a rotating polarization in your domain wall. That would explain such a signal. So again, we said, okay, second harmonic generation, that's nice, but can we confirm that the wall is really not easing-like, but has a Néel component, a Néel-like component, polarization rotation. So again, we did transmission electron microscopy, and indeed, there's the wall. So here you have up polarization, then it rotates slightly, and then you get to the other direction of polarization. Here it's sketched. So we have up, then it rotates, it also becomes smaller, and then it emerges on the other side with the opposite direction. So it's a mixed Néel easing-like domain wall. At the same time, polarization rotates and it becomes smaller. That's something that you can really otherwise not see easily, unless you then do your transmission electron microscopy. And it's only there for these C domain walls up to down. It's not there for these 90-degree domain walls A to C. Finally, and that's our newest approach, and the last thing I will talk about today, second harmonic generation as a tool to monitor the growth of materials. And as an introduction, so how to motivate this. So if you build, so we have a technique that allows us to monitor film growth. That's electron diffraction. So you send electrons onto your growing epitaxial film structure, and then you see how atomic layer by atomic layer the film grows. And you see resonances that indicate the different monolayers, number of layers. But basically what you see is you build something layer by layer, like here a wall, and you can also see that the wall grows nicely, but what you cannot see is the functionality of this whole construction. So you see that your film is growing, but you don't see does it what you want to in the end in terms of electronic or magnetic properties. So it's a little bit like growing a building and not knowing what kind of building you are building. So here's an example. So you put brick on brick, but you don't know are you building the Berlin Wall or the UN headquarters. So create something that destroys freedom or creates freedom. So we need a tool that tells us this transfer to thin film growth. We need a complement to electron diffraction that yields the functionality of a growing film while it grows. And in our group we have Morgan Trassin, who set up all this pulse laser deposition growth, and he is now doing this. So he is combining a laser with a pulse laser deposition apparatus in order to watch samples grow and functionalities like ferroelectricity grow along with them. So this is what Morgan did. So he took his PLD, he sends in, well, first he has this electron beam that creates electron diffraction, and he also sends in a laser through the windows of the machine. And then hopes to see that it can see ferroelectricity, interface properties, and the like, ferromagnetism, antiferromagnetism emerge while this film grows. And he got the funding for that from an ERC project. Okay, here's what we did. So this is our laser. We couple it into the machine. This is just another sketch. We put the digital camera at the end to detect the second harmonic signal. And now we can clarify questions like when you grow a ferroelectric film, how does the ferroelectricity emerge? Gradually with a delay? Or jump like at a certain critical thickness, or does it go up and down because something weird is going on? Polarization domains moving and the like. And in principle, if this works well, you can then also grow arbitrary sequences of polarization. So you can say, okay, my first layer should have up polarization, then up, then maybe down. And a second harmonic experiment done in situ while the film grows would tell you this, because 3 ups would lead to a 3 times the increase of the second harmonic intensity. But if you then grow a down polarized film, the second harmonic wave has the other sign. That means it interferes destructively with the existing signal. So your total signal would go down again when you reverse the polarization with respect to the other layers. That's the idea. So first he tried some very well studied ferroelectrics and checked that. So he took bismuth ferrite and barium titanate. And just grew the film, taking, while it grew, second harmonic intensity and comparing it at the same time to his weak pattern. And he sees, well, yes, after about 2 nanometers, so a few unit cells, your bismuth ferrite develops ferroelectricity, and then it goes steadily with the film thickness. Likewise, barium titanate, after a while, after a few nanometers have been deposited, you start getting a polarization, spontaneous polarization that then grows with film thickness. And it's really ferroelectric. So if you then take out the film at this stage, you can write with a force microscope a voltage into that film, and you see you can polarize it one or the other way. And before this was really laborious. So people had to grow a film of 1, 2, 5, 10 monolayers, take them out of the machine, see if they are ferroelectric. So they have selected samples, and they then measure the ferroelectricity on these samples after they have been grown. Here you see it while it happens continuously. Okay, that worked nicely. So one other remarkable thing, so in thin films, because of the strain and the induced dipoles, you can have grossly enhanced critical temperatures. So typically the Curie temperature of barium titanate is 125 Celsius. Here it's at least 650 Celsius. So that's another amazing effect that you have when you grow strain films. Okay, so here is then this other idea. So he then said, okay, now let's try and go uniformly polarized layer by layer on top. So always substrate, a metallic layer for screening, and then the ferroelectric layer, another screening layer, ferroelectric layer, another screening layer, and so forth. And then you can see, yes, all the bismuth ferrite layers grow uniformly down polarized. They like to do this, and the different layers are not coupled. So in all layers, first one, second one, third one, fourth one, always after something like 4 unit cells, your ferroelectricity emerges. The layers are really decoupled, but because of the metallic interlayer. But you can also do it the other way around. So you can say, let's choose a different termination for our interlayer. So then you can make it happen that the first bismuth ferrite layer goes up polarized and the second one down polarized. It's even a little bit independent of what exactly you do for achieving this polarization reversal. So this is really a very general process. But then, long story short, so you can control what the polarization in each layer is, and seeing that it really is up in the first layer and down in the second, and also making sure that this doesn't reverse when this one is grown. You can see when you track the growth by second harmonic generation. So in the first layer you have this continuous increase. Then you grow your metallic interlayer that absorbs a little bit of the light. Then you grow your second, now oppositely polarized layer. You have destructive interference of the two interharmonic contributions. And after a while, the two signals compensate. If you just look at this film at this stage, you would say there is no ferroelectricity because there is no SAG. Now you know it's just two ferroelectric contributions, two layers that compensate in their second harmonic emission, exactly two signals. So that's a nice tool now to do lots of interesting stuff with arbitrary polarization sequences in multilayers, because of course we can do things like replacing this metallic interlayer by an insulating interlayer, and then these films would start to couple and see each other in terms of polarization, and we can follow all that, and that's what we are going to do in the coming couple of years. Okay, in order to leave a bit some time for questions, summary. So nonlinear optics, second harmonic generation. It's a powerful tool for seeing magnetic and electric structures as well as their magnetic electric coupling. Simultaneously in one experiment. Symmetry is the dominating principle. I didn't go very much into that, but it's all about symmetry. And symmetry cannot be cheated, or there is not a little bit of symmetry. It's a very, very unambiguous tool that helps you determine structures by second harmonic generation. You have access to the additional degrees of freedom of optical experiments. You can image domains, you have spatial resolution, time resolution, dynamical processes, or selectively look at interfaces. And there is a very old review, not the most appropriate one. There should be a new one, and I hope there will be a new one soon. But anyway, if you want to have a look, then you should go to this. Thank you.